Hi, my name is Han Kun Lee. The title of my presentation is Exploring Gaussian Mixture Model for Enhanced Gold Nanoparticle Localization in Photonic Resonator Observation Microscope Image. First, I'm going to talk about what Photonic Resonator Observation Microscope is, and then some of its challenges and the approach to address those challenges. The approach that I'm going to take is actually by utilizing the Gaussian mixture model and the expectation maximization algorithm. So I'll be briefly talk about the Gaussian mixture model and the EM algorithm. After understanding the model, we'll be applying it to the 1D and 2D tool example, as well as to the simulated image by reconstructing the decode model, which is recently published work that utilizes Gaussian mixture model to address the same challenge as PREM. Lastly, I will conclude the presentation. So what is Photonic Resonator Observation Microscope, in short PREM? I won't talk about details about the PREM due to the time constraint. However, it is a microscope that can image single molecules. The example image is shown on the right-hand side, where the single dark spot represents a single gold nanoparticle, which corresponds to a single targeting molecule. The PREM requires localizing and counting the number of gold nanoparticles to generate what we call the dose response. However, the current algorithm is based on OpenCV libraries, which requires manual adjustment of hyperparameters. The reason for this manual adjustment is due to the variation between the batches of images, which causes the algorithms to fail. Therefore, this limitation introduces uncertainties to the system and limits the dynamic range of the dose response. Recently, a group of scientists addressed this kind of a localization challenge using fully convolutional network in a Gaussian mixture model. The model was applied to single molecule localization microscope images. However, the image closely resembled that of the PREM images. Therefore, I wanted to explore the path of implementing the decode model into the PREM system. So this study aims to understand the Gaussian mixture model and its expectation maximization algorithm. Once we have a good foundation of its working principle, we'll be applying it to the 1D tool example, 2D tool example, and also reconstruction of the decode model from scratch and apply the simulated images. Gaussian mixture model is basically a superposition of Gaussians parameterized at different means and variance. Once again, I won't be talking details, but to summarize, the Gaussian mixture model tries to predict the parameter data for each Gaussians by using the expectation algorithm. In the expectation step, what it does is that it computes the expected values of the latent variable, or what we call the responsibility values. These responsibility values represent the probability that each data point belongs to each of the Gaussian distribution in the mixture. After computing the expectation value for the given data, then our next step is to perform the maximization. To maximize the expectation value, we'll be using our good old friend, the negative log likelihood. Taking the derivative of the negative log likelihood with respective to each parameter gives us the equation that are shown below. The first whole example is 1D. We first sample data from two different Gaussian parameterized at different means and variance. Then we randomly initialize the Gaussian to perform the Gaussian mixture model and its EM algorithm. After a few iterations of updating, we can see that the randomly initialized two Gaussians find its way to the right distribution. Next is the 2D tool example. In this 2D tool example, there are 10 different Gaussians, and after applying the EM algorithm, we can see that the model correctly predicts the likelihood of each data point. The third example is where I implemented the decode model from scratch and applied it to the simulated image. This picture shows the overall structure of the decode model, but for the purpose of this report, I only reconstructed the last part of the model where there is a single unit and three different multi-hit outputs. Three different losses are combined to train the model with higher accuracy, and these losses include the count loss, localization loss, and the background loss. Here is a simulated image, which to some extent resembles images from the PREM. I created 1,000 training images, but each image will have a random number of Gaussians. This picture shows some of the outputting images that the model predicts during the training. I want you to focus on the red highlighted box. The image on the left top corners are the ground truth image, and the images on the right shows what the model predicts. So we can see that the model was able to correctly predict what the center of Gaussians are. So in conclusion, we learned about Gaussian mixture model and its expectation maximization algorithm. We also learned how we can apply the model to localization of particles from images. It is a great approach to address the localization challenge of the PREM system. That concludes my presentation.